webinar. It is part of the CPGIS organized educational webinar series and is co-sponsored by CPGIS, NSF Spatial Temporal Innovation Center, Urban Institute at Tsinghua University, School of Geography at Jiangxi Normal University, China Data Institute, and Future Data Lab, and lastly, a Journal of Computational Urban Science. Today's talk features global urban land dynamics monitoring, as you see from the flyer, by Professor Gong Peng. And Dr. Gong is chair professor of global sustainability at the University of Hong Kong. Um, a, um, a short bio introduction here. His major research interests include mapping, monitoring, and modeling of global environmental change, and modeling of environmentally related infectious diseases such as COVID-19. Dr. Gong, I'm not going to pronounce the other diseases since I do not know how to pronounce that. And also a very important aspect of healthy and sustainable cities. He is the author and co-author of over 600 articles and 8 books. He chaired and co-chaired 8 Lancet Commission reports on climate change and health and healthy cities in China. Lastly, and probably most attractively here, Dr. Gong is not only a very well-established educator, but a pioneer CPGISer and also a long-term supporter to our community. So it is our great pleasure here, and also it's a great match to have him today. As a quick highlight, the talk will focus on remote sensing and urban land dynamics. While decades of efforts have been made to map and monitor urban land changes, it is not until recently that global mapping and monitoring of cities have come into being. So Dr. Gong will present a trajectory of urban mapping and change analysis, mainly based on his research conducted. And then he will discuss some possible future perspectives in monitoring the world's cities. Before I pass over to Dr. Gong, just a quick reminder to the audience. Please don't mute yourselves. I'm probably already muted there. Send your questions to the chat room anytime when you have. So after the presentation, Dr. Gong will answer your questions accordingly. So that's kind of a quick framework today. Dr. Gong, please go ahead.
Okay. Thank you, Cui-Zhen, for the introduction. And also thanks to friends in CPGS, particularly Shu Mingbao, an old friend. Can everyone hear me?
Yep, pretty good.
Okay. So now I'm going to share the full screen. Let's see if I can do that. With Shu Ming, he's just the kind of people that I feel hard to reject. Every time one has come up a suggestion, I can only follow him. So, but this one actually is some subject that I feel really comfortable and happy to share with colleagues about my experiences. Like what you already saw in my abstract, I said it's a personal. I keep being requested to do a sharing. I guess I'm not going to be interrupted. I'm going to just say reject. Okay. I hope those who are requesting this wouldn't mind. I'll just keep going. As you can see from my abstract, that I try to comment about the past 3 decades of effort on mapping and monitoring of urban land and land change. that has been accompanying me for my career. Because at the beginning, later I will show you basically my career path, which is a main track of my research for about 15 years. At the beginning of my career and also at the end of my career. So in the middle, I went out to do something else. But I'd like to use this opportunity to present the works, telling you some historical stories with my experience and share with you on some future perspectives. I listed here a few papers on urban land use classification. This is at the time that when I was a graduate student. As you can see, if you can see the cursor here, this is the first paper that I published in a journal paper I ever published. So it appeared in Remote Sensing of the Environment in 1989. The reason I have this paper here is because there's a continuity of the kind of work that I've been doing starting from that time. You see probabilistic relaxation method. At that time, we call land cover mapping, actually it's using an urban setup. Basically, in the old days, when remote sensing just came into being for land application, people began to use spectral information. Now it's a common knowledge that we need to use spatial data, we need to use texture, we need to develop contextual methods. This is basically the line that I've been doing during my doctoral research. Just to share with colleagues here that at that time, I basically tried all these terms. And at that time, the state of the art methodology. So you can see there's a knowledge-based approach to convert from land cover, which is more or less a pure physical evidence of the surface, to land use, which is a cultural concept about human recognition about land. So that's a definition difference. So how do we use land cover as the intermediate result to help us to derive or transform from land cover to land use? Is at that time, we already used artificial intelligence technology. Those who are now in the deep learning field or machine learning field, using the neural networks. At that time, people are using neural networks already. Anyway, there are some papers I listed here. I don't want to go for everyone, but I want to share with colleagues that you need to be careful when making your own terms, trying to define your own field. If you are like me, some of the important work will get buried and nobody pay attention to. This, to me, is the most important piece of work, frequency-based contextual classification and grid-level vector reduction for land use identification. Because I tried not to be using, at that time, the popular term of land use classification or land use mapping, I purposely tried to use land use identification. And also these jargon words of frequency-based, grid-level vector reduction didn't really help me to make people fall, attract people's attention to read this paper. Actually, this is contains the most innovative work during my doctoral research. So that just gave my younger colleagues some advice that don't try to be creating new terms. You can develop new content, but don't try to create new terms in the title, because if you do that, people will have very little attention to it. This is indeed the case. Even though It's very well reviewed by the photogrammetric engineering and remote sensing reviewers, and eventually won the ERDAS Remote Sensing Award of ASPRS. But later, people didn't really, not many people pay attention to this paper. So from the probabilistic relaxation work, in 2006, actually, I have the fortunate to work with Desheng Liu, who is now a professor in the Ohio State University. So we developed a method basically to help do the spatial temporal consistency checking, and also using the spatial neighborhood to adjust make the decision for the central pixel, but using the temporal data and also spatial neighborhood to adjust the likelihood for the particular class. Basically, this is an approach that has later been popular, that people are trying to use spatial temporal consistency check, which is a logical check, and also do the probability adjustment to modify through iteration about the categories so that you can gain a temporal continuity and consistency at today's wide availability of rich availability of satellite data in the time domain. We are able to enjoy this kind of technology to help us to develop more consistent maps so that you can do change detection. Now, here is an example that in 2019, MODIS land cover product collection 6. This is basically the last version of land cover product derived from MODIS data. At Boston University, they eventually adopted this kind of spatial temporal consistency technique to improve their product because they develop annual data set. So this actually trace back to a long time work, developed by our group and later spin off at Ohio State University. This is a paper basically I tried to say which didn't really attract a lot of attention. From the raw data, you need to do grid level vector reduction. It's a smart way to do that. Later, it leads us to step from the grid level vector reduction technology, a fast clustering. In 2013, we published a paper called CBEST, clustering eigenspace transformation, for short, CBEST. It's a new clustering algorithm, which is very efficient in terms of timing. For those of you who have run k-means or ISO data, those kind of clustering algorithms, takes forever. But if you do this approach using CBEST, the paper is published in ISPRS Journal of Photogrammetry and Remote Sensing, is using this particular data reduction algorithm and then allow us to do clustering on this basis. So it's much faster. But at that time, I use an approach basic to condense the data in multiple to make it into one dimension. Then use what we call frequency. You can think about just a histogram to characterize different type of land cover or land use. Eventually, you get a result like this because it's a spatial contextual technique. Compared to spectral approach, such as maximum likelihood classification, and applied to the original multispectral data, you get a pepper and salt type of result. And when you compare the classification accuracy, the difference is about 15% improvement. So using a new technology allows you to develop a faster program and also more accurate results. I stopped working on this as you can see, in 1992. I bet for those of you in the audience who come to attend this particular topic on urban dynamic study would not be unfamiliar with global human settlement layer, GHSL, developed by the European colleagues. And now they are trying to do also annual global annual human settlement layers. So actually, if you look at their method in their report, and also in earlier their publication, trying to use making the effort to do global build up area recognition, they actually used our method, my method during the doctoral thesis. You can see in the term, he's saying the method applied here for automatic information extraction benefits from the seminal work done in the early 1990s by P. Gong and others on the use of image structural information for improvement of recognition of rural-urban fringe. So I'm just trying to say that even though you stop doing things, that other people may find it useful and continue to work along the direction. And actually, eventually, it helps us to do global work. In 2012, I have the fortunate to work with a student, Li Congcong, who is joining Beijing Normal University, basically looking for a subject. So I suggested to her that there's a problem in, lots of people could do mapping, but they don't really study the sample size and their relationship with algorithms. So I advised her to do thousands of experiments at that time on the PC to compare, as you can see here, a number of traditional algorithms, maximum likelihood, nearest neighbor, linear regression, cart trees, classification trees, and gradually moving into those machine learning algorithms such as random forest, support vector machine, and later we also included a neural network algorithm out there. At that time, 2010 to 2015, deep learning wasn't that popular. So we used some of the algorithms and tried to compare that using Guangzhou 8 land use classes and collected samples very carefully done with the help of Dr. Sun Yat-sen University's Professor Li Xia. He actually helped us to do the field work. And eventually, we came up with a paper published in remote sensing, which is about the comparison of which is important, sample size of the training or algorithms. We find that sample size difference could lead huge variation in classification performance. And if you look at the algorithm, we have another chart to have the statistics, you will feel that their differences are smaller. So that actually lead us to give more emphasis to sample collection. And particularly sample size is an important issue in large area mapping, which guided us to do improvement in land cover mapping. So Congcong Li, after this work, she was so tired of urban land mapping, but she was invited to improve the global land cover training samples. It took her a year to finalize a validation data set, more than 30,000 locations all over the world. So that's the kind of work that with the help of a student that you can further test urban land use mapping and with a whole bunch of different algorithms and see which one is performing better, and also how representative and typicality issues in samples could help us to improve the performance of classification. So some of my work are mainly focusing on three things. One is, can I make the algorithm running fast? Two, can I make my classification results more accurate? Three, can I save space? I have to tell you at a later stage that nowadays we have a lot more data sets, and saving data is actually both challenging and also very meaningful. But no matter what, we need to migrate onto cloud to do computing. So anyway, this work also was remarked by Arthur Cracknell in his collaborated work in a few papers, saying that this work is a seminal work. So I tried to share with colleagues that we need to develop algorithms and make our efforts worthwhile so that people feel that you are among the first, or somehow you are doing some work that is useful to others. So with that, I can jump to some, originally we are mainly focusing on uh, optical sensors. And gradually we try to expand the type of remote sensing data set. Of course, one easy hanging fruit we could get is nightlight data. So this is a student class project at Berkeley. When I have the fortune to work with two graduate students, they are now all professors in United States. For example, Emily Ye is in the University of Boulder at Colorado, University of Colorado at Boulder. So when they're in my remote sensing class, we tried to experiment with different threshold setting and try to make it automatic to determine a way to be adaptive to different areas of urban boundary extraction. And then compare that with more higher resolution, such as TM data. You can trace the boundary so that you can see how accurate the adjusted threshold method is. And this kind of technology now is very popular. And we published the work in 2003. And later you can see people like Wong Qi Hao and other scholars are using this kind of methodology to develop their urban boundary studies. And we also use watershed segmentation works to extract both village and urban boundaries. And later we developed along this line to do larger area boundary extraction. Some of the early work we did include mapping all the cities in China on different time. So these are works that are about 10 to 12 years ago. At that time, satellite data are not that readily available as today. So we have to be very selective in using of the data. In recent years, I think colleagues may find it's easier to track our work. I have the fortune to work with Li Xuecao to develop a different set of more threshold-based, knowledge-based, and classification tree-based or experience-based technology to map urban dynamics. So this is the first paper, Xuecao. Xuecao has been very productive. During his time working in my lab for only 3 years and 9 months, got his doctoral degree and also 10 publications. This is one of them that he published about a 30-year record on an annual basis to track the entire Beijing using Landsat data. So after 2013, we begin to have more and more Landsat data available. So we are able to do this kind of annual work. So this technology, as I said, is more an empirical feature composite and thresholding type of approach. But eventually, it leads us to develop a more consistent methods to be able to map larger areas. For example, this paper is allowing us to do the whole China for all the human settlement include urban and rural areas. And this work eventually lead us to do the whole world. Its annual map, we gave it a good name of Gaia, Global Artificial Impervious Area. So for more than 30 years. So basically the method can be extended to any time now if there are new data sets. So in another direction, we try to use social big data to help us to further differentiate inside the urban boundary. What are the land use types, land use categories? And this method now we are expanding it into mapping essential urban land use categories in the whole China. Now we are working for the whole world on a land use map for every individual city in the world. We tested a few methods. Bin Chen is taking the lead on testing it in United States. So we are doing this, and hopefully within half a year to a year's time, we will be able to finish for the whole world about the essential urban land use categories work. So here, I'm not going to show more detailed results. Those who are interested, you can take a look at these papers. I only have 13 slides, so it's almost over. Before we are using various kind of remote sensing data to track urban dynamics in 2D. We look at land expansion or shrinking, the kind of changes in different cities. I shared with you a story. Basically, we start from single city. Now we are doing global work. And in the beginning of the century, a freelance writer called me from Boston saying that he noticed my work on mapping urban areas, but he wanted to know whether or not I can estimate the amount of cement and steel, the different kind of construction materials that has been used in different areas in the world. I thought that's a very stimulating question. I answered him, I said, oh, having only the 2D information is not enough. You need to know urban height. You need to know the structure height. Colleagues, anyone who is in the audience, if you have some experience working with urban planning offices or working with land registry offices in a city, wouldn't be feel short of information about the detailed building height information, because people need to file registration and apply for a construction permit in order to make their building erected in reality. But if you try to share the data, you know, those urban planning and administration department will not share their data with us. So actually, urban height information is very rare. We have to use, you know, a third-party method to do that. You can imagine if you try to do that for the whole world, it's going to be really hard. So in 2009, I started a project with a friend of mine, basically a group of my students, and also Professor, he's a friend of mine indeed, who is actually going to the school with me together, but a few years ahead of me at Nanjing University. So I asked him whether or not we could use you know, satellite-based LiDAR, you know, measurement to measure the height of cities. This is the first paper that is using satellite altimetry to measure cities. So it's published in 2011, basically. So at that time, I find it's a miracle. We all know ISAT is not created for the purpose of mapping urban area, monitoring urban area. It was created to measure cloud height, ocean current, ocean height, sea level height. And also people expanded that. It should be supposedly to do ice and snow monitoring, but people also used it to measure tree height. So we tried to use the LiDAR poles to measure building height. But the poles, the footprint is too big. It's about 60 meters in diameter. So it's a little hard, but we try to work with that and try to estimate, we tested this method in Beijing. We find at that time, most of the glass data ignored the center of cities. I don't know for what reason at that time. So I hope the situation is changing, but I don't know who is going to continue to work on this. I'm a little bit out of date nowadays on this particular direction. But Xuecao Li picked up to use the SAR data of Sentinel to develop a method to estimate building height, average building height, not individual buildings, but within a certain area, say 500 meter by 500 meter location, you could estimate the height of the buildings. So for example, in order to do this, you need to have some idea about some cities. You already have the city height information. So these are the kind of data that we have used in a few places and to calibrate the model so that you can eventually map the urban areas in the world. So basically you need to calibrate using sample data and build a regression. And the input data is from Sentinel-1, which is SAR, using the VVH polarization data to develop this method. And eventually, we extended this method to map all the city height of the world. So this is some samples taken from that. And Professor Zhou Yu from Iowa State University is leading the effort to map the whole world using this kind of technology. So that's all I'm sharing with you for the past on monitoring urban dynamics, land, and also their landscape in terms of elevation. So other than that, we need to look into the future. So some Bay Area engineers are saying that using 3D printing, that they could use their circuit design methods to make cities. They're thinking that they could do something in the desert, build a 1 million population city. So you can see that today's technology is enabling people to have various kind of thoughts on, having these balloons to help us to collect fresh water, having solar panels to power up offices or communities. So these are all in design phase, and people are, with big tycoons like Ma Huateng or Elon Musk, they could spend money partly into this kind of experiment. So future cities will be more dynamic. You might actually move a city, just like moving a big, war vessel, 航空母舰. You can move them into different places, or movable cities on the ocean. So that obviously require more frequent and more flexible mapping and monitoring. And in the meantime, we need to be more innovative. So there are other small issues, but it's important for us. Recently, Professor Sun Yifei from Cal State University in Los Angeles, is working with us, trying to find those 开发区 in the cities, the newly expanded developing areas specifically devoted for industrial innovation, industrial parks, commercial trade parks. You know, if you look at in different cities, you can see that how intensively the 开发区 has been developed. And using our essential urban land use categories map overlapped on top of those city approved districts for further development. You can also find out whether or not, if this is industrial park, you find they are mostly residential areas. There's something wrong. If this is industrial park, you go there, that has been approved in 10 years or 20 years ago, but it's still empty. It's also something going wrong on there. So recently, we are working on this kind of issues, you know, looking more detailed into the city. And also I'm working with one of my graduate students, Nihao. So her name is Nihao, but in English is Hao Ni. On where are the older towns in the cities? Are we able to detect them? Because they are shrinking, they are gone. According to Xi Dada, you know, we want to remember our beautiful, precious, younger age memories. We want to recall that. We call xiangchou. You know, if you go to a city, you find it's totally gone. You know, your home memories has been totally gone. This is something that we are all experiencing today. So where are the ungone areas in China? So we're building algorithms and methods to detect that. For those areas that are undergoing change, you can see that starting from land being cleared and then become new modern structure. So these are the kind of things we can not only go global, we can also go local to look at more detailed things. But we go local not just for the purpose of discovering what is happening at the local. We also want to the trend into the global. If you want to do that, you need to do very detailed data archiving processing for every city with very high resolution of the data. Then we are entering into a big data era. That makes us to think about innovative algorithms to do that. So these are some future perspectives. You know, big data makes ground truthing easier. Some additional data could be collected by other people through cross-sourcing and share with us. Just like, you know, in the 1990s, that University of Washington came up with an idea saying building Roma in a day. You know, using volunteers' pictures, we can reconstruct the 3D structure of all the famous places in Roma for the city. Using fast, you know, technology, you can do it in a day by collecting the data from the internet and then restore the data in 3D. So these are the kind of things that we need to go out our boundary to comfort boundary, to go out our comfort zone, to work with others in an interdisciplinary manner, to take their knowledge and technology and apply it to solve our problems. So I'm actually inspired by this group of people saying building Roma in a day. I said mapping the world in a day. Indeed, we are able to do that. Even with 30-meter resolution, we could use a supercomputer to map the world in a day using 1,000 cores of the supercomputer. So that's the possibilities with today's technology. Today's technology enables us to build innovative future cities. Today's technology also enables us to monitor the cities in more innovative, frequent, and flexible ways. So we also need to rethink about in the future, how do we organize our research? Should we keep working in a small research group? I've been interacting recently with Professor Xiaoling Zhang from City University of Hong Kong. Lots of her collaboration work are done through working with others in different parts of the world. She is, organizing a small research group at City University of Hong Kong, but her productivity last year is more than 40 papers. So another trend in the future is cloud computing, which is, for large area mapping, we need to rely on cloud computing. So we actually have done some work. If you look at this year's remote sensing environment, we just have a paper published on IMAP World version 1. That means we mapped the whole world's land cover on an annual and seasonal basis using Amazon Web Services, using 100,000 cores of their Amazon computer. And we were able to produce petabyte level data, process data, and come up with seasonal level land cover data from 1985 up to now, 2020. So all of these are possibilities in front of us, colleagues and students in the audience. So I think we have infinite possibilities to work into the future. So presented work are mainly the major collaborator, not exhausting the whole list, but include Xuecao Li. He graduated 2016. He's now a full professor in the China Agricultural University. Teng Yunhu is a urban planner. Bin Chen has just recently joined Hong Kong University in the Faculty of Architecture. And Hao Ni is still a graduate student. So thank you very much for listening to me. Now we can discuss. Yeah, Cui Zhen, I'm done.
Yep, thank you for this excellent talk here. For the audience, if you have any questions, please print to the chat room. Dr. Gong can see that. Yeah. When you are submitting the questions there, actually, Dr. Gong, I may start the first question here. I want to echo what you just said in the beginning. Do not try to create new terms in the title and develop new concepts instead. I fully agree with this, and I think we all have kind of similar experiences in the past probably decades. Um, the problem is for nowadays, so it's not like we want to create or we can create new terms, but rather we are surrounded by new terms like big data, big earth data, big climate data, big social data, social sensing, earth sensing. We see these terms come and go, and most of them cannot stand long. So from your experiences here, what's your suggestion to the next generation younger scholars? So what they should focus on the terminology here?
Well, thank you for I just want to advise young colleagues. It's not a bad idea to create new terms. It's just that I feel that some really important work by me using identification, when people try to search land cover mapping, land cover classification, they would miss my land cover identification. So they will not be able to see my paper, which, of course, today is totally different. That's 30 years ago. Now we are entering into a much faster world. So some terms might be fashion. Fashion come and go, but there are also timeless, terms that people will use forever. So if you are the lucky one who leads the current and created a term everybody follow, there's a certain reason for that. But in most cases, like what Cui Zhen said, terms comes and go. It's like a fashion. We either go with the current, then people will pay attention. Anyway, it's not. I probably made something only to those young people. When you have an important work in your titling, you may not try to make it too out of the current. Follow the current, use that, and people will pay attention to your work easier. So that's my point.
Thanks.
Thanks.
Any other questions here?